Hey everyone, how you doing? It's me, it's Clara. I'm back with another one of my science chats. So in these videos, I'm chatting to my friends who are awesome scientists or engineers or mathematicians, and we're going to find out a little bit about what they do, where they work, how the work environment is for them, and maybe chat a little bit about equity as well. So today I'm really excited. I've got Dr. Clara Nellist, who is a particle physicist at Cern on the Atlas project. So that's super exciting. Anyone that's been sort of looking at my videos on what we use superconductors for, I actually talk a little bit about particle acceleration, and I talk about how we use superconductors to bend the magnet, to create magnetic fields for making sure that our particles crash into each other at the right place, basically. And so Clara is actually working on that kind of stuff, so that's great. So before we start, Clara's got a YouTube video channel, and is on the socials and stuff, so check down below for her links. Give her a like and a follow, and of course like, subscribe, share this video if you enjoy it. And with that, we will move over to the video.
Yeah, hi, I'm Clara. I am a particle physicist working on the Atlas experiment at Cern, and I study all particles and how they interact with each other to try and understand what the universe is built out of.
Yeah, that's really succinct. That's awesome. And also, like I say, we know each other through some of this sort of outreach and the diversity and inclusion work. So tell us a little overview, and we'll come back to that later, but a little overview of the stuff that you're involved in.
Yeah, I guess to also try and keep it succinct, as I was progressing through physics, I noticed, of course, that that there's a lack of diversity. And initially I was looking at women in physics, and so I wanted to encourage more women in physics. And as I have progressed through my career, I've noticed that it's not just about getting people into physics, but it's creating an environment where everybody can thrive and really flourish with their research. So it's also about keeping people in physics, and now I've broadened out and understanding the different diversity that we need to include in science.
That's wicked. Yeah, that's something I was talking about with Andrew. It's really nice that I started out looking at sort of LGBTI plus in STEM and maybe working class in STEM, and it's broadened out. And actually, I like the fact that we are being more sort of intersectional, because it means we're not just trying to improve things for one group, we're trying to improve things for everyone. And it means that, well, intersectional people exist as well. So
yeah, and it's a fight that we're stronger if we work together. So we shouldn't just be focusing on my area or this one area, but if we work together and make a really substantial change, then everybody can benefit from it.
Completely agree. But this is why we're all friends. I think we're in many ways on the same page, and yet we're not scared to call out each other and say, no, I have a different viewpoint. It's nice that we're able to actually sort of criticize and make each other think, and we're all willing to listen, which is really cool as well. So but I'll come back to the science first of all. So I noticed your background. Is that from where you work, per se?
Yeah, so this is the Large Hadron Collider at Cern. So this is part of the experimental setup that we have. So it's a 27-kilometer long tunnel. So if I went that way for 27 kilometers, I would end up back in the same spot.
Okay, so it seems like a good workout.
Yeah, I really want to run it, but they don't let you, obviously, because it's quite a sensitive environment. But I'd love to do a 27-kilometer race through the tunnel.
Yeah, I understand why they don't, but also, yeah, they should.
Yeah, I think there's a virtual video of going through the whole tunnel, but I'd have to dig it out.
Wow. Yeah, I should point out I could not manage 27k 27 what is it, 27 kilometers or miles? Sorry.
Yeah, it's kilometers. Yeah, so a little over half a marathon.
Yeah, no, a few years ago I was like, you know what, I'm gonna get myself to the point where I can run a half marathon, and I was doing 10k's, but then my knees unfortunately won't let me run anymore. So it is what it is. So I'm much better hanging off rock faces and climbing instead. So anyway, oh, and like I say, I get sidetracked a lot, so I apologize in advance. So yes, so you work at CERN. How long have you been there? And you talked about the Atlas project. So what does that do within the sort of projects at CERN?
Yeah, so I have been working on experiments at CERN for over 10 years now, but always with the Atlas collaboration, the Atlas experiment. So along the LHC tunnel, we have 4 major detectors that have slightly different goals in the research. And 2 of them, Atlas and CMS, are looking for, we say it's general physics. So we collide protons together at the center of our detectors. And then we measure everything that comes off of them and try to recreate what was there at the center. So it could have been a Higgs boson, it could be many of the standard model particles that we know of, or it could be something new. So it could be dark matter, it could be other kinds of physics. And I started, so my PhD is actually working on the detector itself. So I started upgrading the detector. So the very heart of the Atlas detector is made out of pixels, and my PhD was on developing new pixels so that we could take even better data. And now I work more on the analysis side, so studying the different particles in the collisions that we produce.
Oh, that's fantastic. I hadn't realised you'd been working on it so long. I wasn't sure, because some people, obviously, I've been in my current group 5 years, and I was in all different groups before that. So you've been on the project some time now.
Yeah, so I've moved to different universities. So I started at the University of Manchester, and since then I've had different postdocs, but it's always with the same collaboration. So it's kind of strange because you change countries, you change labs, you change groups, but actually the work you're doing can be either exactly the same or very similar. So it's kind of nice to still have that continuity.
Yeah, I find the same thing. I worked in a lot of labs, and every so often I'll be like, I'll just get this. Oh no, that was a different lab. I don't have that here. But yeah, no, that's really interesting. And it's fun to, I don't know, I like moving around. It's good. So does that mean a lot of the stuff that do you spend a lot of time, because you've been in different universities, do you spend a lot of time on site at CERN, or do you do a lot of offline work as well? How does that work?
So it's a bit of a mix. When I was doing a lot of hardware work, I really needed to be in the lab that I was with, because we had clean room facilities where we would test our detectors in-house. And then we would spend a lot of time either at CERN or at DAISY, which is in Germany, which is another particle accelerator lab, where we could do the actual tests within the beam conditions with our detectors. So as a PhD student, I was based at CERN for a full year, which was really great to meet people and to get integrated into the community. And then since then, I've spent a lot of time going back and forth. So I spend, say, about a third of my time at CERN and the rest of the time in the lab or the university.
Oh, that's cool. That's cool. Where's Daisy?
So Daisy's in Hamburg, so just on the outside of the city.
Okay.
Yeah.
I've only travelled through Hamburg Airport, I think. That's about it. So, okay, cool. And so, so where are you now? Where are you based now? And I realise this is a leading question because you're sort of in between, right?
Well, so I'm still with the same. So I'm currently in Nijmegen in the Netherlands. So this is where my university is. I'm with Radboud and also with NICEF, which is the Dutch high energy physics funding. And so I'm still going to be with them, but I'm moving to CERN to be based there for a while. So yeah, kind of in between locations.
Fantastic, that's great. So I'm fascinated about CERN, and I've got a little bit of an idea, but my first degree wasn't physics, so I'm always sort of, I think we were talking about this recently. I was trying to double check that some of my stuff was right.
But yeah, I mean, even within CERN though, I mean, I have to do this too. So it's such a huge facility and there's so much going on that we can become experts in this one thing and then something else happening in the accelerator research or on one of the other experiments. I have to go and ask people to explain that to me, or we have a discussion about it. So it's very common. There's so much going on that you can't possibly know everything, to be honest.
And it's a big facility, but yeah. So I've worked with people that work with making the superconductors. Obviously, being in the Centre for Applied Superconductivity at Oxford, and I've worked with people that are involved in making different coatings for the inside of the tubes and stuff like that. So I've worked with sort of the materials thin films groups, and it's really cool and really interesting, and it is amazing just how. I mean, Cern is such a massive facility, obviously. Like you say, it's 27 kilometres. Is it a big campus? Is there campuses in different countries at that stage? Or
Yeah, so actually we have two main campuses. So we have the main one, which is in Switzerland, although within that you can cross into France and back into Switzerland again without leaving the campus. So we have a little stone that says when you're going into France. And then we have another campus that's actually just in France, which is where, for example, the control center for the Large Hadron Collider is. So a lot of the accelerator physicists are based on that site. And then a lot of the detector people are based on the Meyrin site, which is in Switzerland.
That's so cool. I love the fact that it's like, oh, I'm in another country. I hadn't realised where I'd wandered. That's really cool. I love that.
And people forget when they go to the other site and there's a restaurant there that you have to pay in euros, whereas on the main site you pay in Swiss francs.
Of course.
So you can pay in the other currency, but sometimes the exchange rate isn't so good. So you want to pay in the correct currency for the country you're in.
Yeah. And having been a postdoc in Switzerland for 4 years, is the canteen in Switzerland about 5 times as expensive as the one on the French side?
The good thing about Cern is that even though it seems expensive when you get there from somewhere else, if you then go and eat in Geneva, it's actually quite reasonable, the cost compared to eating in town. So it's a bit more expensive than the French side, but it's not a massive difference because they try and keep it reasonable for people.
Yeah, we actually, I was doing some experiments. We got a short-term project from an EU cost action to allow a professor from Belgium to come and work with me in Zurich. And they have a very set amount that you can, for sort of daily living. And that wasn't even half the cost of the cheapest hotel I could find. Yeah. So they ended up crashing in my spare room for a couple of weeks instead. But yeah. But that's by the by. Cool. So what is it you're doing on a day-to-day basis? How often are experiments running? How often are you smashing things into other things? And is that a rare occurrence?
You mean for my work or just in general? How much do you smash stuff up? My favorite comic. There's a great comic that has it says, if biologists did their research like the LHC or like Cern, and they just smash 2 frogs into each other and try and look at all the pieces, which I don't recommend doing because it's not very nice to frogs, but I thought it was quite funny. So day to day, I'm doing analysis work now. So we're not currently running at Cern. We're in what's called a shutdown period, which is a scheduled block of time for about 1 or 2 years, where we warm up the accelerator, open up all the caverns, and we install our upgrades, we do repairs, we maybe improve. So the accelerator, if we want to move to a higher energy, it also needs to be trained, the magnets. So all of this happens during the shutdown. And so during that period, we're not, for example, doing shifts in the control room. We're not monitoring the detectors, but we're still analyzing the data that we've taken before. So we have a huge chunk of data that we're sifting through to try and do precision measurements, to try and find new particles, to do all of the studies that we want to do, ready so that when we take more data starting next year, then we're ready to add to the data we've already got.
Yeah, that's really cool. It's ironic that you mentioned flags. I just chatted with Andrew Prinsep, and he was talking about levitating frogs. Go figure.
We don't levitate any frogs. So day to day, I'm doing a lot of coding. So a lot of writing scripts to search through the data to select events that we're interested in, and also I'm starting to do more machine learning work, so writing algorithms to select for me, because there's so much that we have to consider. So all the different features of the event that we could say, okay, I want 1 electron rather than 2 electrons, and that will look at a certain set of data for us. We can teach machine learning algorithms to do that in a more intelligent way, in a more powerful way.
So you're not just using a microscope and, you know, looking really hard. That is a joke, of course.
Yeah. Although we do sometimes say that the LHC is like a huge microscope, because it's really looking at things on a tiny scale. So we don't look with our eyes, but we often use the analogy that it is like a huge microscope.
Funnily enough, as I was saying it, I was actually wondering that, because that's effectively what you're doing. I mean, you are, like you say, looking at very small things, or very, very small things, in fact. But yeah, and there's a lot of crossover with some of the work that I do, but obviously it's a very different scale. And the idea of a 2-year shutdown for maintenance, I can imagine that the researchers in my lab would not be so happy if I said that we had I'm just going to do some quick maintenance. The system will be up and running again in 2 years. I mean, most research positions might not even be that long.
Yeah, so we have a page that tells you the status of the LHC, and I like, so at the end of the last shutdown, they usually write, so sometimes we have shutdowns for, say, a day, but that's not shutting down the whole of the LHC. It's not doing collisions for physics analysis, but the accelerator physicists might want to do some beam studies, for example. And so they'll put a little note on this page, you know, shut down for beam studies or whatever. And at the end of the last set of run, they wrote shut down for intervention, estimated time 2 years. So
wow, yeah. And I know, I mean, a different bit of kit, but I was at Culham in the UK, at Jet, looking at their fusion generator, and I was there when they were sort of trying to get it ready to turn back on after a long time. And actually, the next time I was there, they just fired it up like the day or so before. I was there doing some trans awareness, and I got to see them firing up Jet, which was pretty cool.
That does sound very cool. I would love to see that.
Yeah. Don't think I was supposed to be there, but they were like, yeah, whatever. It'll be fine. So I love it, and I'm also getting to learn all this different stuff as well, which is fascinating. So you said that you're so basically particles are being sort of smashed into each other, not frogs particles, and then you're measuring them. So how are you smashing the particles, and how are you measuring them? And I realize that is a lot of information, so feel free to talk about in whatever depth you feel happy doing.
Yeah, so we have the protons in the accelerator, and the accelerator physicists work on making the bunch of protons really dense together, because that means that when each beam crosses each other, you want the chance of there to be an interaction to be very high. And so the denser the proton bunch, we call it, the more likely you'll get a collision. So that's what they work on, and they also work on making sure like the crossing angle is right to increase the chance of collision. So they accelerate the protons to very nearly the speed of light. We get them up to what's called 13 TeV. It's a tera electron volt, and it's the center of mass energy of the collision. And then using Einstein's equation, E equals mc squared, so we know that matter can be converted into energy and then back into matter again. So we take the matter and the energy from the protons, they collide together, and from that a new particle is created. So the rate of the particles being created depends on what you're colliding, the energy that they're colliding at. So we can predict all of this. And then a lot of these particles are not very stable. So for example, the Higgs boson doesn't hang around. It's not a stable particle. So it will change into lighter particles from the standard model, or perhaps outside the standard model, which would be wonderful.
Yeah.
And then these lighter particles travel out in sort of a firework shape. It's not a firework, but that's kind of the spray that it comes out as. And as they travel through different parts of our detector, which are specialized for identifying and measuring the properties of different particles, it's then like a fingerprint. We can say, okay, we had these types of particles in this section of the detector, and they had this energy, and we add it all back together, and we can say, okay, there was probably a Higgs boson there. So we can never say for certain what was in the center, but we can predict from what we measure. And we do this billions of times, and then we put it together in these fancy plots, and we say, okay, there. So for the Higgs discovery, for example, we looked at, you can look at the rate of 2 photons coming out of the detector. And this happens for lots of different types of events. And so you get a nice falling graph as you increase the energy of the 2 photons. And then you get a little bump at 125 GeV once you collect enough data. And from that bump, you can say there was a particle that was decaying into those 2 photons. It had a mass of 125 GeV. None of our other particles have a mass of 125 GeV, so it's a new particle. And so that's one of the ways that we discover new particles in our data.
Wow, that's so cool. It's, I mean, and like you say, it's a lot of energy. So I tried to do a very basic overview of it in a video that should be going out fairly soon, actually, on my channel, which you kindly looked over and corrected. But it's so complicated. There's so much different stuff going on and so many different theories that and especially not coming from a physics background, for me, it was like, it was a learning curve.
Yeah, but I will say that one of the misconceptions we sometimes get at Cern is that it's only physicists that are working there, but we really have a massive team of engineers, computer scientists, material scientists, and then that's also to mention we have lawyers and human resources staff and translators. And so Cern is tens of thousands of people, and we really need everybody to come together to make this happen. So the person who gets to make that final plot and say, I found the particle, gets, a lot of the credit often, but really there's such a massive team behind the whole endeavor. And I'm sure I've missed groups out. So, we have firefighters on Cern. We have a dedicated firefighting team, just so that we don't set anything on fire, or if we do, they come and stop it.
Yeah, actually, when I was doing my postdoc in Switzerland, my office office mate's dad was one of the health and safety inspectors at CERN. So kind of his dad was part of one of the parts of the cogs in that machine, and we were talking about it before because I was talking about usually I work with material scientists, and even within the material scientists there's the coating groups and there's the superconducting group, and there's so many of those. There's so many different people. It's quite remarkable just how many people are there and how much effort goes into making the experiments work. Which is why I don't know if any of our viewers have looked, but when you've got a paper, there's like 2 pages of people listed on there, but it's because there is so much involved and so much going on. So
so just quickly, the example that I gave with the Higgs to 2 photons, so it's not, you also have to do a lot of calibration and understanding, for example, of are you measuring the photons correctly, and are your detectors working well, and how do you read out the data? Are you collecting the right amount of data? How do you store it? So all of these questions have to be answered well before you can make that final study, and that's why there's so many teams. And so everybody in the collaboration who's done any contribution to the collaboration then gets to have their name on every future paper, because you really can't say that just one team made that measurement. It's such a huge team effort. Yeah,
absolutely. And it's like I say, it's such a large piece of kit, so of course it needs a lot of people. I'm all well and good maintaining a few vacuum chambers in my lab, but you're vacuum chamber is on a literally another scale.
Yeah, I think don't we have it's a bigger vacuum than outer space? You think? I don't know. I know it's colder than outer space at the LHC. I'd have to double check the vacuum, but it has to be a very good vacuum because any sort of stray particles or dust that's in the accelerator can degrade the measurement.
Yeah, absolutely. So my equipments are just sort of high vacuum or ultra high vacuum, and then you've got space. And I think I can't even imagine the size of the vacuum pumps or the type of vacuum pumps you've got working at the LHA. I've not actually had a look around, so
you have to come visit.
Yeah, I believe it or not.
Live tour.
Yeah, I've even. So I streamed a video that was talking about sort of LGBTI in STEM, and that was being streamed to a group in Cern, and I've worked with so many different people. I've even lived in the same country, and half the same country, and I've still not managed to.
But you're in the German-speaking part, right?
Yeah.
Yeah, it's very, very different part of the country.
It's amazing how different Switzerland is across its relatively small length and breadth. It's quite amazing, but I did have a nice time there though. And it is beautiful being surrounded by mountains. Oxford's far too flat for my liking. Someone that climbs and hikes, I like a bit of mountain. And so the one question that sort of occurs to me, and this is probably a really basic question, but I'm putting you on the spot, so maybe it's not. So you're sending these particles around the system, and like you said, it's 27 kilometers long. So how long does it take them to do a rotation?
So the frequency, that's a good question. We collide bunches 11,000 times per second, but that's not necessarily because we have a whole train that's in the beam. It's say a tenth of a thousandth of a second. Did I say that correctly? It's very, very quick.
Yeah, that's incredible. And do they when I was doing my animations, I had them going round and round and round. Do they go around a few times, or do they go around once?
Well, so it's 11,000 times a second. So if you had one bunch, I'd have to check the numbers completely.
Oh, no.
But yeah. So, but then we have the beam in the LHC for hours. So I think there is a record of the LHC, which I think is over a day of having beams circulating in the collider. So it's billions of times that they will or more go around the accelerator. And really we eventually would just get rid of the beam and start again, not because we can't keep it in the accelerator, but because when they collide it reduces the number of protons that we have, and it's more complicated to try and top that up than to just get rid of all of it and then to feed in a whole fresh bunch of protons.
That's so cool. I love it. And I mean, I'm sure all those particles are getting really, really dizzy going around there. Ironically, I've just been looking into spin, so there's sort of a little bit more to that. But I'll sorry, I got completely sidetracked there. Okay. My own silly mind has just gone sort of spinning off. So I'm trying to refocus and think of something intelligent to say. So is there so you're collecting an awful lot of data, and like you say, it takes you years and years to go through this data. I mean, you must have, I can imagine the computers, the storage and those things must be huge. I mean, there must be an intense amount of data.
So we have our own dedicated data center, but then we also have copies that are distributed all over the world. A, for backup, and B, so that people can access them from anywhere, access the data. That's
really, really cool. I'm gonna ask a question that possibly sounds a little bit flippant. And I always sort of hate this question, but it's interesting. Why are we doing it? What's the point? Why are you doing it?
Good question. I do it because I'm curious, and I think that part of the human endeavor should be to understand our surroundings and what we're made of and how everything interacts with each other. I want to live in a society where we value this and where we progress towards it. But also, I mean, so the primary reason is curiosity. It's just purely because I want to know how everything works together. But it's nice that there are benefits that come from it. There's technology that is developed. I mean, at Cern, we're doing things that have absolutely never been done before, and we have to invent new technology and methods to be able to do it. And because we're publicly funded from countries all over the world, everything we do is open source. So all of our papers are open access. Anything that's invented is just there for people to use. So touch screens were invented at CERN. The web is one that we commonly talk about. PET scanners are, I don't think they were invented at CERN, but they were the technology that we use have benefited PET scanners, so proton emission tomography scanners. So I also like that the research that we're doing feeds into this sort of open culture of knowledge and access to technology. So that's why I do it.
No, that's a really good point. On one side, it's important to know because those discoveries will help us understand other materials, other properties down the line. And so there's no science that is completely isolated. Like, even if you're looking at materials that people aren't specifically interested in at the time, something's going to come from it. But yeah, it's a really, really good point that you made about the technology. We don't think because we're trying to do something new and you're trying to do something at the cutting edge, we have to develop new techniques. And I know on a sort of smaller scale, but we talk about Formula One, which is obviously a business, but there's so many developments that have happened in Formula One for racing that have then gone on to road cars, and so like hybrid technology and stuff like that. And I didn't know that touchscreens were a CERN thing.
Yeah, in the 70s, there's some great like retro footage of like this really old screen that they're touching. And I should dig out again. There's a story, a motivation behind why they wanted touchscreens in that situation. But I'd have to dig it out to know the story. But I know that they were invented at CERN.
That's really cool. I had no idea.
Which is one of the reasons why it's free, because there's no patent that means that you have to pay to use it. So the design was just, here you go. Thanks for the public money. Here's some new technology.
Wow, that's amazing.
Yeah.
And this is what we're talking about, nothing happens in isolation. I mean, my PhD was working on materials that are used in touchscreens for a sort of next generation. Well, potentially next generation anyway. I don't think my PhD, as is often the case, science doesn't always give results.
Yeah. But that is a result. I often have to tell people that just because you didn't discover a new particle, for example, that we had to look. So that was a result. That's a good thing to have done. It's not as exciting as having a discovery, but everybody contributes, even with negative results.
Actually, that's a really good point that I'd sort of like to, just sort of talk about, because this is it. I think it's really important that even when you have those negative or null results, that is such a huge, that is, like you say, that's learning stuff, that's improving science. But there isn't the culture of writing papers behind that, and it's actually sort of dismissed. And I know that when I was starting out my PhD, I found results after 2 years, sort of null or negative results after 2 years, and other groups are like, oh yeah, we knew that, but they didn't write about it. There weren't any papers.
That's rubbish, because if we did that in particle physics, we would be going round and round in circles if people didn't publish when they got no results. So I think it's really important to tell people, I looked, I didn't find it. So then they don't look in the same place.
I love that you're talking about CERN and you're talking about particles going around in circles. Sorry, giggling to myself. Yeah. Oh, yeah. No, that's good. So is there more of a culture of publishing sort of these null results and negative results? Because that's just not something I come across in my field.
Yeah, we publish. If you do a Google search for consistent with the standard model, you will get almost all of our papers. In fact, all of our papers. No, almost all. There's some inconsistencies that we are still teasing apart. But yeah, consistent with the standard model is we didn't find what we were looking to find. If it, for example, it's beyond the standard model physics or supersymmetry or dark matter. Currently, everything is consistent with this one model that we have to explain how most of the universe works. Well, not most of it, but most of the matter part works.
Yeah, I like that.
Yeah.
I actually like that. I wish we had that in more fields because, like you say, we'd save so much time, and so much research is publicly funded. Like, why are we not putting that information out there?
And people spend a lot of time on it, and they deserve to be able to say, look, I didn't get the result that I was necessarily looking for, but the method was very good, and maybe they developed new techniques for the method for searching, or, with the machine learning, I could run my machine learning algorithm and it could say, yeah, sorry, everything looks normal here, but the algorithm could be very good and interesting for other people to look at. So that's still a result, even if you don't find a new particle.
Yeah, no, yeah, it's a big thing. I mean, my PhD didn't put out, it wasn't paper worthy in many ways, and yet I did a lot of experiments. My thesis was packed, and it's really annoying when groups sort of 4 years later find a little bit of extra information, and it's like they can publish stuff, and it's like, I did 90% of this, I just didn't get the sexy results.
Yeah.
I didn't get the sexy science. So yeah, it's yeah. So speaking of discoveries, you've been working with CERN for 10 years. Is there anything that you're particularly excited about that you've achieved or discovered or proved isn't discoverable, or what's your CERN highlight?
I mean, my personal highlight is we just put out a paper looking at the 4 top quarks created at the same time. So we don't call this a discovery because it's a standard model process, but it's a measurement of this process that had not been done before. So the measurements had been done, but we set limits on how often we think it could happen. So the theory tells us we expect it to happen this amount of times, and we say, okay, we haven't measured it more than 3 times what you predict. So that's called setting limits. And now we have a measurement that we call evidence, which is 3 sigma confidence, 3 standard deviations confidence of having this prediction. So it's a precision measurement. It was really difficult to do. It took us over 2 years to do this measurement. And so I'm really proud to have been part of the team that did this measurement and contributed to this really rare measurement. I mean, obviously, we also have the Higgs Discovery, which was very exciting. So I was a PhD student when that came out, when that was announced. So I was working on the hardware, so not directly involved in the analysis, but we decided that, so there was a group of the students at CERN at the time, when they announced the announcement would be in the auditorium, we knew that we weren't going to get seats because loads of them were reserved unless we got there very early. So we turned up at midnight for a talk that started, I think, at 9 a.m. the next day, and had a bit of a party outside of the door. And so I was about, say, the 20th person into the room. And so I was sat right at the back in the middle of the auditorium and got to hear the presentations, the discussions, and just the feeling in the room of the community as something that people had been looking for 50 years. So Higgs was there, Professor Peter Higgs, and Professor Francois Englert was there, and the other theorists as well, who were part of the theorists who predicted the field and the particle, and then just so many people who'd been involved in the discovery in different ways were in the room. So it was just really exciting. It felt like being at a rock concert, queuing up the night before and saying, "Oh, I really hope we get a seat and we can get in there." And then afterwards we went into the restaurant at Cern. I fell asleep because I barely had any sleep, so I was like this on the table. And a journalist came up to our table, which woke me up, and said, "I could tell you are British. I could see the Pims from the other side of the restaurant. Does anyone want to talk about this result?" Mm-hmm. And so I said something, and I don't even remember what I said, but that was like one of the first articles I was quoted in, because I was like, "This is great. I'm so happy."
That's amazing. I love that. Yeah. Wow.
It was a fun day.
Yeah, that would have really been something to be a part of, and sort of, you know, I mean, yeah. It's the God particle, right?
No, we don't call it that. I'm not allowed to say that. Know. You can say that. I'm not.
I can say that. No, I know. I was going to make another joke, but I think I'll probably not.
You can make it. I couldn't.
No, actually, I'd rather not. Always avoid religion. So I'm gonna switch tack a little bit.
Okay.
So, like I say, we know each other through our work in sort of outreach and diversity, trying to push for equity in science for different people. So, how's your journey been in STEM? Has it? And you don't have to talk about anything you don't want to, obviously, but you know, how's your journey been? Has it been okay, or have you seen stuff that you're like, I don't want anyone else to go through this?
Yeah, I think so. As an undergrad, I think I was pretty ignorant. I knew obviously that there weren't very many women in physics, but because I was at the University of Manchester and it was such a big physics department, we would have the women studying in physics, we would sometimes meet, or there would be events, and so it didn't actually seem like that few, because say there were 30, that seemed like quite a lot, even though there were 250 people studying physics in my year overall. And so I just, at the time I was just focusing on my studies and didn't really notice it. I think as I've transitioned to a scientist, to this being my career, and I've become more aware, I have noticed a lot more, situations where I think, oh, that wouldn't happen if that person wasn't white, for example, or the number of times people get interrupted in meetings, how comfortable people would be in a situations, and jokes that can exclude people, and then also through doing more of the equality and diversity work and talking to other people and hearing about their experiences, that's also made me more aware. So I think it's very important for us to educate ourselves, and I wish that there had been less time spent when I was an undergrad teaching me how to cope in science, and more efforts on how to break down the barriers that meant I would have to learn how to cope.
Yeah, and it's sort of interesting what you say. I was talking to someone else and they were like, oh, my experience was fine because I'm a cis white male. And I was like, yeah, but, did you have any trouble because of your sexuality? And it was like, oh, well, yeah, but it's not as bad as other people. Like, we have this really messed up baseline. Like, It's like, well, at least, we're here. And it's like, well, at least this isn't happening to me. But that doesn't mean that the people down here are experiencing that.
Yeah, but also as a cis woman, they often, you get asked to be involved in things, and so that sometimes makes you feel a bit special, and you don't realize until later that you were being tokenized and that you weren't actually being supported and given resources. They just wanted to show how many women they had. And so now I don't want to do any more training of like power stances and how to project my voice and stuff like that. Now I want to focus really on what are the barriers, what are stopping people from just doing great science and being happy and having an environment where people can be creative. Because if you're stressed all the time about whether or not a country that the conference you want to go to, whether you're persecuted there because of your gender identity or your sexuality, or then that's not the best way for people to be able to be in science. And then that's how we lose people, because some people just say, I'm not doing this anymore, I'm going to work in a different industry where it's not well, sometimes it's not so bad, but some people don't have a great experience.
Yeah, I think and it's interesting what you were talking about. It was, I think, early approaches to diversity were more like, we're willing to have you, just make sure that you conform and be like us and do the power stance.
Yeah.
And yeah, I heard that a lot sort of a few years ago. I hope that people are realizing that we shouldn't be trying to change people. I don't know if...
Well, we should change some people, but just not the ones that they usually focus on.
That's an absolutely fair point. Yeah.
I would like them to do how to not be a bigot training. And I know that they sometimes do unconscious bias training, but that usually teaches people, and I've even been involved in it. I've taught unconscious bias training myself. But sometimes you have to be polite to be able to get things through it all. To be a bit more direct about it and say, here are the consequences of your actions, and if you don't learn to be different, like you can be ignorant at the beginning and still have an effect, but if now that you know about it you're still doing those things, then that's actively excluding people from science.
Yeah, I was thinking about this yesterday. I was sort of pulling together some slides on fusion energy, and I mean, we're spending billions, we're putting huge resources, huge time. Like we should have experiments in another 20 years, and we're putting all that effort in the hope that maybe we'll get fusion energy. And yet, when we ask people to change their behavior to improve the lives of other people, it's like, well, that's too much.
Yeah.
It just...
So something I've come to realize, so for example, this analysis I was talking about, the 4 tops, it was such a great experience to be in it. And we spent 2 years going through every single systematic uncertainty. So we would say, this is the way we measure this in our experiment. How does that have an effect on our final result? Could it possibly be something else that is influencing our result, and therefore we're not measuring what we think we're measuring? 2 years of weekly meetings, of emails, of discussions, of conferences, of workshops to get this result. And I'm so proud of this result. But I want us to apply the same rigorous thinking to equality and diversity, and to why, for example, certain groups are not represented in science. And when you try to talk to, not exactly the same people, I'm definitely not talking about my team, but when you try and talk to the same types of people, scientists, particle physicists, and say, oh, hey, look, we're not very well represented for Black scientists in our research. Maybe there is a systematic bias within our community, within the way that, at schools, in universities, throughout the career process, that means that people are not Black people in the UK, for example, are not becoming particle physicists. Let's look at where that is happening. Let's look at what biases are influencing people. And people go, nah, they just don't like it. Some people just don't want to do physics, or there's no problem. And I just don't understand.
Yeah.
That makes me very frustrated.
Yeah, at least, well, yeah, we've got a long way to go, but I think we are improving things. I think
sorry, I don't mean to be a downer.
No. I completely agree. And we were talking about, we have a lot of these conversations. And it's all, how can we improve things? And I am glad that things are moving, but I think that some of that is, we've got a lot more voice, so we've got a lot more, we can be heard a lot easier these days with social media and stuff like that. And so we can't be ignored anymore, which maybe 10 years we could.
Yeah, this is good. And organizing and talking to people in different fields is very good as well, to be able to see what other people might be implementing that could work, and learning from scholars who are really researching on this. So I don't pretend that I'm actually an expert. I talk a lot about it because I'm also quite loud, and once I get frustrated with something, I don't want to just let it go. But there are people whose whole jobs it is to do this kind of work and research, and so I've been trying to read more of their work and citing them basically, to make sure that I'm not just taking somebody else's work. Basically the same as what we would expect of a good scientist.
Yeah, due diligence and sort of, ethically useful references and stuff like that. I mean, it's like I say, I think it's improving. It's great that we've got more of a voice these days, and the internet, it has its flaws, but I mean, because of the internet, some people got together and organised the LGBT seminar that I went to, and that's where I went a few years ago, and that's where I met so many of the people that I was working with, and they've introduced me to other people. So, and I know that I'm not alone anymore. I'm not the only trans scientist out there, which before I really got involved in sort of diversity in Twitter, diversity in STEM on Twitter, I felt very alone. And so it's really great that we can bring people together, because it can be hard work. it can be really hard work.
Yeah, and also I think one of the nice things about the group that we're in is that the people who are being directly affected by something should have a voice in directing it, but they shouldn't have to do all the work. If something bad is happening, if people are being aggressive about trans rights, then we should also, so cis people should also stand next to trans people and say, this is not okay, and take some of the burden, because I don't think it's fair that, it's exhausting to have to deal with things.
I agree, but I also like, so we're talking about the group Tigers in STEM, and I love the fact that I can say something and someone will be like, whoa, no, you've got that wrong, that is not, that's racist or that's ableist, and but we can have a discussion about it, and we'll listen, and I come out more educated, I know more, and improved as a result of that. It's nice when you can, because you don't always feel that people are listening to you either, but I know that within our group, if we say, no, you've got that wrong, it's like, oh, sorry, right, why? And that's really nice, like people being able to say, yeah, I don't know everything, which as scientists, you'd think that was a basic principle. We don't know everything, otherwise we won't be doing what we do.
Yeah, there's that pie chart, right, of things you know you don't know, and things you don't know you don't know. And we need to be better at saying there's this whole chunk of things we don't know, and that's okay, we'll learn.
Yeah, exactly. Absolutely. And just talking a little bit more, so obviously a big part of improving sort of inclusion, equity is just visibility, and I know you do a lot of science outreach, like you're involved in different little things. Is there anything that you'd like to talk about that you enjoy doing in terms of the science outreach side of it?
Yeah, I mean, maybe to start, I mean, this is where I started to get more involved with, because I wanted to show at the time a young woman working in physics as a sort of working example of somebody in the field, because representation matters. And now, so I still do a lot of outreach. I love talking to schools. I do a lot of sort of remote conversations with schools.
Amazing.
Because they can't always travel. Geneva is very expensive to get to. especially during the global pandemic. People can't travel anymore.
Yep.
So being able to still give young people the experience of wonder, of being able to even virtually visit our lab and to understand what we're doing. Because I want people to understand. I don't want it to be this sort of hidden research facility. It's not. It's you can go on tours, you can talk to the scientists, and we're very happy to explain what we're doing. But now also I do work on enabling others to do outreach. So I want, because as you said, representation is so important. I don't represent everybody, so I want to make sure that other people can also do outreach so that they can be representative for their groups, and I think that's important as well.
Oh, that's really good, and I think and that's the basic principle of real equity is giving other people a voice and allowing them to have their voice and giving them that platform. It's really cool. So
yeah, it's the whole imagery of climbing a ladder, right? There's some people that will climb the ladder and they'll just climb on their own and say, great, now I'm here. But there are other people that sort of help the people following to climb up the ladder as well. And that's how you bring people up with you. I don't want to climb on my own. I think that's very lonely. And I think it's important that we bring everybody else up with us.
Yeah, and unfortunately I do know people that would kick the ladder down after they've got to the top as well. So
Yep.
Sad, but I'm loving the image. I mean, do you have like big waddles of school children, like 10-year-olds running around the Large Hadron Collider and poking things?
Not in the tunnel, although we have had open days where people can go down into the tunnel, but that's quite rare. I've only been into the tunnel once. It was quite funny when I went to New York a few years ago, and I went to the UN and had a tour. And while I was there in the canteen, I thought, oh, how strange it would be to just have tour groups in your work canteen. And then I remembered that that's exactly Cern. That's what happens all the time. And I just sort of don't really, it was just so normal. I didn't really think about it. But yeah, when everything is open and functioning without a pandemic, we often have school groups that come and visit Cern, and it's really great. Sometimes they're all in jumpers with sort of sciencey themed nicknames on them, and it's nice to see them. And what I really love about doing outreach and talking to people about what we do is that I can get very bogged down in the code. I might spend all of my day trying to work out one bug, and that can be very frustrating, and you're just working on this very small part of the whole thing. But when you do outreach and talk to people about the work that we're doing, then it reminds me of the bigger picture, the motivation for doing it, and just the excitement on people's faces when you can show them the detector. I also benefit from it because I get reminded of how cool it is that the work that we're doing. So I think it's great to share.
That's really funny, actually, because you were sharing that story about being in the canteen and how strange it would be to have people looking around, and I was thinking, God, I can't imagine having people coming around my lab. And then I realised that normally I have about 10 to 20 schools a year coming to my lab, and I've built demos to show them superconductivity. So you forget. That's interesting, isn't it? It's so embedded and we do it so naturally that we sort of forget that we do it. And I'm often trying to avoid spilling liquid nitrogen on our school children because, that would be a lot of paperwork. So
yeah.
Well, that's amazing. Is there anything else that you sort of want to mention, whether science or outreach? And feel free if there's not.
I think we covered a lot. I don't think there's nothing on the top of my head that I think, we didn't talk about this. I mean, we could keep talking for hours, I'm sure, but I don't think there's a big thing that we missed.
Yeah, no, definitely. I could definitely be talking for hours. It's as simple as that. I'm loving it. But I've taken quite a bit of your time, so I really, really appreciate you coming on and chatting, and thanks for sharing the work you do. And like I say, I'm really privileged to work with you, to know you. I think you're an amazing advocate, and it's great that I've got all these friends that I'm just like, wow, this person's amazing. It's awesome. So thank you so much.
Yes, well, thank you for inviting me on, and the feeling is mutual. I'm so impressed with all of the work that you're doing, both in your research and the advocacy work that you're doing. So it's a pleasure to be on your channel.
Oh, thank you so much. Well, brilliant. Yeah, so with that, I'll say goodbye to viewers. Thank you so much for watching, and I'll catch you again with another chat at some point. And do follow Clara on social medias and stuff. I'll put some links below. So thanks so much again, and take care, everyone. Bye.
Bye.
Wow, that was awesome. That was so cool. So I love these videos, and I get to learn more each time. So thank you so much, Clara, for taking the time to chat. The next video I've got recorded is with Dr. Izzy Jessing. I need to do a little bit of editing on it, but I'm actually hoping to put that out a little bit sooner. I just need to check on the sound, really. So yeah, like I say, don't forget to follow Clara, and if you could subscribe to this video, that'd be brilliant, and I'll see you again soon. Till next time. I almost knocked my cup over, can you believe it? Oh, until next time, take care. Bye.